right, class, today we're going to start chapter 13. This is the final chapter we're going to cover, and it's all about sequences and series. So section 13.1 covers sequences and series, so we're going to get a basic introduction to what these new terms that we haven't heard before mean. So let's take a look at that. So one of the things that we as human beings like to do is we're always looking for a pattern, okay? So can we find a pattern in these numbers above? So let's take a look at example 1. Well, these are just the natural numbers, right? 1, 2, 3, 4, 5. But how do I get to the next number? Well, every time I'm adding 1. How about for example 2? I've got the numbers 5, 9, and 13. So the first thing we always want to do is see if they're maybe like a multiple of each other. Well, 5 isn't a multiple of 19. So how about what's the difference between them? So 5 plus 4 gives me 9. 9 plus 4 gives me 13. So the pattern in this case would be adding 13. A couple more examples for us. So how about here I have 1, 13, 25, 37, and 49. All right. Well, it seems to me that each time we are adding 12. And last but not least, I have 1, 4, 9, 16, 25, and 36. What can you tell me about these numbers? Well, they're all perfect squares. So what we're doing is we're taking the natural numbers and we're squaring them. These are examples of sequences. A sequence is a function that computes an ordered list. And these sequences can be finite or infinite. Okay, finite meaning that they have a number of elements you can count. So you can count them. So they have 5 or 25. Infinite means exactly what it sounds like, right? We can't count them. There's no way. They go on and on forever. So remember that the natural numbers start with 1, right? And a finite sequence has the set of natural numbers as its domain. Okay, where n is the first number in the sequence. An infinite sequence also has the set of natural numbers as its domain, but it has no final number. And we're going to denote n, we're going to use n to denote the natural number when we're coming up with better ways to define these sequences. So let's take a look. One of the first ways to define a sequence is with a recursive definition. Okay, so what does that mean? So we tend to label the elements in our sequence A1, A2, A3, so on and so forth until AN. If it's finite or if it's not finite, it would just go on forever. So I have my A sub 1 defined. Then I say A sub n is 2 times A sub n minus 1 plus 1 as long as n is greater than 1. So let's go ahead and find A sub 2. A sub 2 is going to be 2 times A sub n minus 1. So A sub 2 minus 1 plus 1. Well, A sub 2 equals 2. A sub 2 minus 1 is actually A sub 1, which we have defined. It's recursive because the second term relies on the first term. So A2 equals 2 times 4 plus 1, which is 9. So now I know A sub 2. Let's go ahead and find A sub 3. A sub 3 is going to be 2 times A sub n minus 1. And in this case is 3, so n minus 1 would be 2. Well, I know that A sub 2 is 9. So I have A sub 3 equals, I didn't mean to rewrite that. So I have 2 times 9 plus 1 equals 19. So a sub 3 is 19. So if we started to write out our sequence, I have 4, 9, 19, and I want to find the first 5 terms. So let's go ahead and find a sub 4. A sub 4 is 2 times a sub 3, which is 19, plus 1. That's going to give me 39. And a sub 5 equals 2 times 39 plus 1, which is 79, right? It's recursive. The definition of the second term relies on the first term. The third term relies on the second term, right? They rely on the one before it. That's important to note. That's what makes a recursive definition. So, how could I write the functions for these in order for it to be recursive, if it is recursive? So, this would be a sub n equals n, okay? So, this one's not recursive. The value of our first element doesn't rely on the value of our second element, right? In this case, we're just using n to represent and go through the natural numbers. Here I have my a sub n is not 1, so a sub 1 is 5, and then a sub 2 is 5 plus 4, which is 9, and a sub 3 is 9 plus 4, which is 13, so it is recursive, right? It relies on the one before it. So I can write this as a sub n equals a sub n minus 1, right? Because here was a sub 2 and a sub 3 plus 4. So this one is recursive. All right, let's check out these next ones. So we already found out in the beginning of this section that we were adding 12 each time. So I'm going to have a sub 1 equals 1, and then a sub n equals a sub n minus 1 plus 12. We noticed that these are all squares, so my a sub n in this case is n squared. So this is recursive. Wow, you can't really read that now, can you? Let's try that again. This is recursive, our first example, and our second example is not recursive because the value of our second term doesn't depend on the value of our first term, and so on and so forth. So why don't we go ahead and look at these terms. This one is not recursive, right? Because I did not have to use an a sub n minus 1 to define it. And we're going to find the first 5 terms. So a sub 1, so that means n is 1, would be 1 plus 1 over 1 plus 2, so 2/3. A sub 2 equals 2 plus 1 over 2 plus 2, which is 3/4. Can you kind of see a pattern? What's happening here? It appears that each time n increases by 1, my denominator increases by 1, so it went from 2 to 3, and my denominator increases by 1, so it went from 3 to 4. So this is going to be 3 plus 1 over 3 plus 2. That gives me 4/5. Can you go ahead and guess what A5 and A6 are going to be? I bet you would guess correctly. If I have 4 plus 1 over 4 plus 2, that gives me 5/6. And if I have 5 plus 1 over 5 plus 2, that gives me 6/7. Is that what you'd originally guessed? So here we have the first 5 terms of this sequence. Let's get some more practice finding terms of a sequence. If I have a sub n equals -1 to the n times n, again, this is not recursive, right? Because there's no a's, because there's no a's in the definition. So if I have a sub 1, that's me -1 to the 1 times 1, which is just going to be -1. If I have a sub 2, that equals -1 squared times 2. Well, -1 squared is a positive 1 times 2 is 2. If I have a sub 3, That gives me negative 1 cubed times 3, which is negative 1 times 3, which is negative 3. Can you kind of see the pattern that's going here? We're still going with the natural numbers somewhat, but we're switching from negative, in this case, to positive every other time. Let's try this again. If I have negative 1 to the 4th times 4, that gives me a positive 1, right? Because we're multiplying by negative 1 an even number of times. Times 4 gives me 4. And a to the 5th gives me negative 1 to the 5th times 5, which is negative 1 times 5, which is negative 5. So here are the first 5 terms of this sequence. Let's go ahead and take a look at one more example. So I have a sub n equals 2 times n plus 1 over n squared plus 2. So I'm going to be plugging in my values of n. I have 2 times 1 plus 1 over 1 squared plus 2. That's going to give me 3 over 3, which is 1. If I have a sub 2, that's going to give me 2 times 2 plus 1 over 2 squared plus 2. So I get 5/6. A sub 3 is going to be 2 times 3 plus 1 over 3 squared plus 1. So my denominator is 10. Nope, it's plus 2. My denominator is 11. And my numerator here is 7. A sub 4 equals 2 times 4 plus 1 over 4 squared plus 2. That gives me 9 over 18, which is 1/2. And then I have a sub 5, which equals 2 times 5 plus 1 over 5 squared plus 2. So I would get 11/27.